at the GCC yeah, seminar, monthly seminar. And of course, we're delighted to have Aubrey here presenting again his experience. And of course, Aubrey doesn't require introductions from this group, but it's always good to remember a bit his background. So he got a chem engineer degree from Zambia and then moved to UCT, where he got a PhD degree back in 2006, quite a while ago already. And I was delighted to meet him in person in 2008, correct, Aubrey, in Falmouth in the UK when we met and became friends since then. So, and of course, since 2006, virtually 2008, Aubrey has been engaged with different elements of the group here in the GCC and has been absolutely instrumental to forging this group from the base up. And of course, Aubrey has been engaged. He's a man who doesn't say no very often, isn't it? He's been a chair for the GCC, a chair for ICRA. He is a department chairman for the chemical engineering at the University of Cape Town right now. He's a deputy chairman at CMR, also at UCT. And besides having a lot of research activity, industrial interactions with quite a few partners here. And I believe his presentation today will touch upon exactly some of these experiences that he got from blending academic knowledge and research to actually good field experience with the partner companies. So I guess, Aubrey, you can take the chair and really we're looking forward to that. And just a final news is, yes, I was just let know that Aubrey will be the keynote speaker for next year's Comminution 2023, correct, Aubrey? Which will be held in Cape Town in person. No internet there. Actually, it's in person. If let's hope for that, for success with that. And I think nothing best than having Aubrey presenting, getting that important conference kicked off. So looking forward to see your presentation today. Aubrey, you have the floor.
Thank you very much, Marcelo, for those kind words. And indeed, we are looking forward to Comminution 2023, where we can have some personal interaction. The presentation today is themed Insights in Good Design and Operating Principles for Closed Circuit Meeting Applications. This is basically just a conversation on what are the key areas that we need to focus on when we look at the closed circuit meeting. And let me see if the technology will be kind to me and it will work. Okay. Okay, so when we look at closed circuit meeting or comminution in general, we do understand that it is done in sections. And the reason for doing comminution in sections is to improve both on energy efficiency and also the product quality. Now, for us to do it in stages and achieve energy efficiency and product quality, we need to have a gate who decides what has qualified to go downstream and what should still be retained upstream. And that is where closed circuit applications come in. They are very common. They are used even in the crushing section, even in many downstream sections. But today we are just going to focus on the grinding aspect because it's a very big topic. When preparing this presentation, I tried to cast my mind to all the plants I've been to on Earth, which number in hundreds. I can't recall any plant that does not have a closed circuit loop. All the plants I could remember have a closed circuit loop. So it is clearly a very important subject to talk about. So in closed circuit application, there are two things. One, it's a comminution device. Secondly, it's a classifier. So the question we want to ask is, why is classification important in these particular systems. So one is if you have poor classification, you will have energy wastage, and you will also reduce your capacity. So the classifier would help you in terms of energy efficiency and releasing capacity. Secondly, your recovery downstream, be it flotation, leaching, and so forth, will be compromised if your closed circuit application is not working well. And the point that we typically overlook is that if you have a poorly designed classifier, you will have unstable operations. So your circuit will not run properly. And then you may have also numerous problems downstream. And the one I've picked up here is those who do leaching and even flotation. You find that if the closed circuit loop is not working properly, you end up sanding up tanks downstream. And the tanks that we are referring to here include leach tanks, if your operation is leaching. I had a very good photograph to show you, but the owners of the plant didn't want me to highlight. So silting of the tanks is a big problem in leaching, and it comes from the closed circuit grinding loop not working well. You send coarse particles downstream and it causes that. Flotation tanks also silt if you send very coarse particles. And the other one is the sump that is right at the end of the ball mill or the single stage SAG mill can also sand up if the closed circuit loop is not working well. So it is a key area that one should focus on. So for efficient closed circuit applications, we need to look at two key things. One is the type of grinding and the classifier chosen. So that's key. In other words, the equipment that you have in the circuit is critical. Secondly is a design of the circuit, how the equipment links together. You may have very good equipment for your circuit. If you don't link them properly, then your system will not work well. And the other element to look at is assuming that you have correctly sized your grinding mills, you've correctly sized your classifiers, you've linked them well in your circuit. The other important element is the way they are operated. And by this, we mean the control loop that drives your circuit. So the control of this becomes a key issue. And then lastly, all of this has to be done within the constraints of the ore body. Remember, we don't choose the ore. The ore determines how we can process it and how we can engage with it. So three key things: correct selection of equipment, correct linking up together of this equipment in the circuit, and how you control it. And all of these actually define how a closed circuit application would work. So in this presentation, what I've done is I've selected typical plant examples just to try and help us define what are the insights of setting up and operating closed circuit grinding circuits. So we are going to discuss this in terms of where you have a feed size influence, where you have the ore attribute influencing your system, where you have your classifier, what does it do, and how can you harness the advantages of certain classifiers. And then lastly, we will look at the compression grinding equipment with air classifiers. What can we learn from that? So those are the 4 examples that will orbit our presentation around. Yeah. So before we go for the examples, I borrowed this from the workshop that we did with Malcolm way back. This actually captures the grinding business very well. For instance, we have blasting, which is the first part of comminution. Then we have the run-of-mine ore, which we can also crush to give us a crushed product. or we can use a SAG mill after that, or crushers to give us a feed to the ball mill. And the ball mill can give us the product that we can send to flotation or leaching or whatever we use. But if you look at the energy involved in this, blasting very little energy, and the energy increases as you reduce your size. So this gives us a picture that in terms of energy efficiency, we typically look at this side of the particle size spectra, okay? This side, the energy equation is very forgiving, but once you go here on this side, it's very aggressive. And unfortunately, this is where milling happens, and this is where our discussion centers around, okay? So the first example I'm going to give is the Takwa circuit. What you are seeing here is a grinding circuit is actually the whole plant at Takwa. Takwa is a gold mine, and they use the CIL process to recover the gold. For those who do not know the leaching terminology, CIL is just carbon in leach. Okay, so this is a carbon in leach circuit. They do the mining, as you can see here. Then the ore from mining goes into the primary crushers, and from the primary crushers, they separate into coarse stockpile and auxiliary stockpile. Then from there, it goes to the SAG mill. This is a very unusual SAG mill, very long, 12 meters in length, okay? And it's one of the longer SAG mills. Then after reducing the SAG mill, it goes to a cluster of hydrocyclones. The underflow from that cluster is what feeds the ball mill. The overflow goes to leach, okay? Then from the ball mill, it goes to another set of cyclones, and then the overflow from there goes to leaching. The underflow is recycled to that ball mill, okay? So why are we talking about this example? Well, this example, we are talking about it because at one point, they had a very high throughput with the, they were meeting their nameplate throughput, let me put it that way, and their feed was relatively fine. But when they changed the mining method, they went to what they called a coarse feed. Now, when they did this, the grinding circuit, the performance plummeted. They could not meet their throughput. They could not, they were grinding super fine. And there were two schools of thought on site. One group thought the ore was harder or more competent than what they mined before. The other school of thought, which I subscribed to, was that the ore was exactly the same. However, the blast was different. So there was an issue with the feed size distribution. So we did some surveys and we got some pictures. So these pictures give you an idea. This was a feed before, which was finer. You can see there aren't as many big rocks as you would see on the coarse feed. What you would see in the two pictures here is a complete absence of fines, okay? They actually called this pit Rocco Zero when they changed the mining contractor, okay? And if you look at the SAG mill product, when they had fine feed, the transfer size, some of you who use that term, was about under 1 millimeter. And if you look at when they had the coarse feed, it was about close to 3 millimeters. So this was a huge difference. And because of this, the ball mill would not cope. And these are the pictures from inside the grinding mill. With the coarse feed, you can see all the material was dominantly very coarse. You can't even find fine material here. On the other end, you can see lots of fine material in there. So the subgrade material was plenty on there. Same grinding mill and same. So the question is, how would you set up a classification system or a closed circuit system to help you when you are receiving such a product? Well, their classifier was robust enough because remember that the SAGMU had, the SAGMU product went to a classifier, only the underflow went to the BOMU. So because of that, the BOMU product went to a different classifier. You can easily tune it so that the product quality is the same. And this is exactly what they did at TAQWA, or what we worked to do. So the nameplate capacity for this was 1,500 tons per hour. When the feed, before they changed the mining method, they were doing 1,600 tons per hour. After changing the mining method, 1,200 tons per hour. This represented a huge loss in terms of income, okay? Then we also instituted that because they couldn't change the mining contractor, we added a pre-crushing stage to reduce our feed size. And you can see that after we did that, they went to 1,760 tons per hour. So the mechanics of what we did and how we did this are a subject for another day. Today, we just want to emphasize how you utilize the closed circuit application. In this particular circuit, we ensured that we tuned both sets of cyclones so that we can have a consistent product. And you can see from the product here, the circuit P80 was almost identical. It didn't matter what we did to the feed. And you can see the percent sub 75 microns, it was right where we needed it. So this particular system showed us that you can, irregardless of what a feed would be, you can retune the circuit to give you a consistent product. And when you do that, your recovery would be exactly the same. What you may lose is the tonnage. For instance, where you had coarse feed, you lost in terms of the tonnage, but you did not compromise your leach circuit. Now, there is one thing that I wanted to mention here. This is after optimizing the classifier and the meal together for that feed. Before that, the plant was struggling to even do 900 tons per hour. So after readjusting the closed circuit loop, the plant was able to release a bit of capacity within the feed constraints to produce the material that was desired downstream. And these are the PSDs from the system. And the leach recovery was around about 93–94% for all the surveys that we did with those different feeds and the different closed circuit application interventions. Okay. The second one I want to look at is, we are still staying in West Africa. This is a single stage grinding mill. The single stage grinding mills are actually preferred in certain plants, but for these mills, they rely on one mill to produce the final grind. So you don't have a second mill. So the system that has a grinding mill and its classifier would produce the final product. It lacks flexibility because you have to control both the grinding mill and the classifier for you to actually get the circuit to work well. Both the throughput and the fineness of the grind are in this closed circuit loop. That's where they are controlled, okay? So the classifier in this circuit has a huge influence on what you do. And a lot of effort should actually be put to organizing how your classifier does the reject and the accept. So I'll give an example in another gold mine here in South Africa. In this gold mine, initially they had what they called lazy cyclones. And these lazy cyclones were actually used to perform your classification. Then later, they replaced the lazy cyclones with the more modern cyclones. This is just a picture to show how a modern cyclone looks like. It was a different design, but a more modern design that they had applied. The advantage of a more modern design is that most of them, they use a bit of CFD to see the flow. So there's no flow disturbance within the system. And because there's no flow disturbance, it gives you a fairly good cut size, and the balancing of the material within the cyclone is done properly because there's no mixing that induces breaking out the classification that you've done. Okay. So in the initial design, there were two things. One is it was a wrong size, very big. And then secondly, it promoted very high circulating loads. And then the PAET from the circuit was coarse and the throughput was lower. So when they changed the hydrocyclone design to a more modern one, they had better performance both in terms of throughput and fineness of the product that went to the leach circuit. Here are some of the specifications for that particular plant. So it's a small gold plant. They were initially, with the original design, they were doing 115 tons per hour. Just changing the cyclones, they went to do 145 tons per hour. You can do the maths. This is a huge improvement. The energy consumption was barely the same. The circulating load, look at this, it reduced from 440% to 340%. This is a huge reduction, but the win came here. Can you see here the PAET reduced from 100 microns to about 80 microns, and the leach recovery moved from the mid-80s to mid-90s, which gave them more money because of this. The other thing that happened, other than just changing the cyclone, was to also change the control. So the control for the circuit was changed. For instance, the grinding mill looked more at the load as a primary control other than the power, which was the initial case. And then the hydrocyclone, they looked at controlling the flow to the hydrocyclone at a consistent density. And this resulted into this huge gain in the performance of the plant. Yeah. So what could go wrong in these single stage mills closed with hydrocyclones? I have a few pictures here. One of the things that could go wrong is if the grinding loop is not working well, you will have slurry pooling, okay? And slurry pooling is induced because of mainly three things. The first one would be the design of the grate. The second one would be the feed that you are introducing into the grinding mill. And the third one is an incorrect design of the classifier. And all these three can cause slurry pooling. If you have slurry pooling, you lose your power, okay, because of the counterweight, you lose your grind, and your circulating load increases. So your whole milling circuit does not work well. You actually go into instabilities. So I have three examples here, three different mills, which all had slurry pooling for different reasons. The one at the bottom was because the classifier was not working well. The one at the top, the grate design was not properly done. And the one in the middle was the feed composition was not properly arranged for this type of application. So all the three are illustrated in those pictures. This affects the low aspect ratio mills greatly because it's a long mill, and if the transport is impeded, then you go into slurry pooling, which becomes a big problem. And in the graph there, it just gives you a test that you could do if you are in slurry pooling. If you are in doubt, just switch off the feed for a bit. And if you switch off the feed for a bit and you see the load plummeting, going down aggressively, and the power shooting up instantly by a huge margin, then you are in slurry pooling. And if you are there, then you have three things to look at. You look at how is my feed, how is my grate design, and how is my classifier design. The classifier design is very easy to note because you will see circulating load will be high, very high. And when you open, you have a slurry pooling. Then you know it's a classifier. If you've been on a plant where they are scared to open, the grinding mill, because they say, well, the slurry will come out on the feed end. That is a telltale sign that you have slurry pooling, and there could only be two reasons. One is a classifier, secondly is a design of the grade. Okay, so I have an example here where again we have an inefficient grinding
webinar. The webinar, the Mainza webinar.
And in this particular grinding system, one, we have an inefficient set of cyclones. Then secondly, we had efficient set of cyclones. So the throughput for the inefficient set of cyclones, 775 tons per hour, just reducing the circulating load from nearly 600% to 300, you could see they had a gain in throughput and a gain in the grind. And what I did not mention here is the silting of the tanks actually completely stopped because they had that problem. The bigger gain was in the grind that they achieved, which released capacity, and also the leach was performing better in this particular system. Okay. So the next example I wanted to just look at is a system where you could replace hydrocyclones with screens. Okay. So we are looking at how do two different classification systems fare. Okay. Let me just plug in my computer. Thank you. So the hydrocyclones usually are forgiving because they can accommodate a wide range of of conditions. They are very low on maintenance, and they can match a wide range of throughputs. So for a given hydrocyclone, if you look at the volumes that it would allow, it is quite a high range. But they are inherently inefficient because they rely on the hydrodynamics to effect the separation. Some particles would always bypass into either an overflow or the underflow. So the coarse particles would bypass, go into the overflow, and they would cause problems downstream. The fine particles would be trapped and follow the water to the underflow, which represents inefficient. So they may lead to overgrinding. Screens, their limitation are the footprint. They require a very large footprint to accommodate a bigger plant. And usually when you apply them in single stage closed circuit, you need a high footprint and a very good control on the feed. Particularly if you have fine screens, then you need something to protect the fine screens. And it's been shown, and I may show a slide here, that efficiency decreases with aperture size. So as you go smaller, the efficiencies decrease. Then there is also a problem of blinding of apertures. Okay, so these are all issues that you encounter with screens. In short, the decision whether to use a hydrocyclone or a screen depends on what you want to do. Okay, because they both have limitations and they both have the strong points. This is an example on one of the gold mines in Namibia, where the hydrocyclones were actually replaced with the screens. And what you would see here is that the closed lines and the closed markers represent the hydrocyclone. The open markers represent the screens. So you could see that in terms of the final product, the screen had actually a coarser product compared to the hydrocyclone. Okay, so if you look at the SAG mill product, this is a single stage SAG mill product, the screen was fine at the fine end, but coarse at the coarse end. Okay, so typically one would say, well, both systems had very little plus 1 millimeter in the downstream circuit. Okay, but what you would note is when we had the hydrocyclone replaced with the screens, the throughput went up to 140 tons per hour from 126 tons per hour. And the product was coarser, as I said earlier. The circulating load reduced from 160% to 45%. Screens usually run with very low circulating load. The energy was almost the same. And in terms of the footprint, it wasn't an issue on this plant because they had a spare space where they could put screens. Okay. So the one element I wanted to bring up is that when you run particularly high frequency screens, you need to be very careful with the percent solids that you operate them at, because the efficiency of the screen decreases as you run at high solids content. Yeah, so you can see here the alpha decreases with the increase in feed percent solids to the screen. So this was for different tonnages. We ran experiments at 9 tons per hour for a small derrick screen and all the way to 19 tons per hour. So when you again increase the throughput on that screen, the efficiency decreases. And the reason is the material form a layer on top of your screen, and any material that has to reach the aperture has to percolate through that layer. So the other material, it acts like a bed, and you have to percolate through to reach the bottom of the bed in order to be presented to the aperture. And that is why we have this reduction in capacity. We also did this with the 3 different aperture sizes. So what you could see is that the smaller aperture, the D50 decreases with increase in feed, and so are the bigger apertures. But again, if you run at very high tonnage, the effective aperture is reduced because of the load that you are putting on the screen. This is an example of a screen that is not working well. Okay, so if this screen is not working well, the 2 problems could be: 1, incorrectly sized aperture. So before you pick the aperture, you need to know, will this material run through this aperture without clogging up like you've seen here? And if it does, what would be the tonnage for this particular aperture? Then secondly, for rheologically complex ores, they tend to clog up the screen from about 300 microns all the way to the fine material. So if your ore has rheology issues, you need to do something before you introduce it to the screen. Some of the people use desliming ahead of the screen because of the problem that is presented here. Okay. The other problem is this is not a high frequency screen. This is a standard screen. The apertures for this particular screen were just under 1 millimeter. Okay. You can see it's clogged up. Okay. And the reason for this is the screen could not just cope with the throughput. And if it doesn't cope with the throughput and it clogs up, then the whole plant has to stop. And the cause for this clogging up could be: 1, a higher throughput than the screen; 2, the spray bars not spraying well, it compromises the whole screen. But the point I wanted to emphasize is if the screen fails, the whole plant fails in this closed circuit. While we don't pay attention to screens, it's one of the things we should be paying attention. Where you have screens, do not use processed water in your spray bars because they clog up easily. And once that is done, the whole plant has to stop on a simple thing like spraying over the screens. The second, the topic I want to look at now is the ore constraints. And I've picked my favorite ore in this particular topic, which is the UG2 platinum ore. The UG2 platinum ore has two constituents. The first one is chromite, which has a high SG, typically about 4.8. And then it contains silicates, which has a low SG. It's typically 2.7, but because of the contaminants in the silicates, you can get silicates and compounds that go with it at about 3 SG. Okay, these coexist in the same ore. You can see in this particular picture here, the chromite is usually darker. You can see from the top there. The silicates is very light. And since this is a platinum ore, the PGMs are associated with the silicates. The chromite is barren. But you need to now effect your classification and your recovery in the ore that contains both. Currently, if you purify your chromite properly, if you recover it and it's of a high purity, just the sale of the chromite in this particular ore can give you money to run the whole plant. Basically, the PGMs would be a profit. So it is also important to separate out the chromite so that it's a sellable product, and then the PGMs associated with the silicates. Okay. The problem is what I alluded to earlier, that there is a density difference. If you use a conventional cyclone, the chromite will always report to the underfloor, even if it's fine enough, to create a huge circulating load, leading to reducing your capacity for the mill, because you're now grinding a high circulating load, and you're wasting energy because that chromite is already ground. Okay. Secondly, in a cyclone, the silica, which is light, will escape through the overflow even if it's not fine enough to have liberated PGMs in it. So when it goes downstream, you will lose recovery for the PGMs because of that problem. Okay, so let's apply that to a circuit. This is our MF2 platinum circuit. MF2 means you grind, you send it to the primary rougher float. After floating the tailings, you again grind them, and then you send them to the secondary rougher float. So that's what MF2 means, okay? So this part is a primary. You can see you grind here, and in this particular plant, this was a bore mill. Then you send it to the primary rougher float. The product, you introduce it in a sump, it goes into a classifier, then the underflow from the cyclone, you grind it, the overflow, it goes into your float, okay? So that's a closed loop. In this particular case, you see, we have a closed loop, grinding loop for primary, closed grinding loop for secondary, okay? So the UG2 effect is impacting on this circuit twice. But today we want to focus on that loop on the secondary grinding, okay? Here, the capacity is dependent on how efficient you can classify in that cyclone, okay? So that cyclone there controls the quality and the reduction of overgrinding. What I didn't mention earlier is if you overgrind the chromite and it escapes through flotation, it will be entrained into your concentrate. So if it goes to the smelter, it's a penalty element because your energy in the smelter is compromised by having the chromite. Apart from that, it forms what they call spinels in the smelter, which are also a problem in the smelting. They affect the separation of the matte and the slag. Okay, so it has many consequences in your smelter. So many different cyclones have been tried in that particular application. What I'm showing here are the conventional cyclone that was tried and the flat-bottomed cyclone that was tried, okay? So you would see that if a flat-bottomed cyclone is used and the data shows that these are partition caves, okay? And these partition caves are for the overall, which is the middle line, then the chromite, which would be the dotted line that way, and then the silicates. So for the flat-bottomed cyclone, you can see it is these dotted lines. The middle one would be the overall, which is the composite containing chromite and silicates. Then the top one would be for the chromite. The bottom one would be for the silicate. You can see the cut size for the silicate is very coarse, okay, at the D50 here. While the cut size for the chromite, even for the flat-bottomed, is slightly finer, but coarse compared to the conventional. It's also steeper. So in this particular case, you can actually say the conventional cyclone was doing better than the flat-bottomed cyclone. Okay, so the myth that the flat-bottomed cyclone would separate based on density is completely dispelled by the many data sets that we have. And this one is also highlighting exactly the same point. Okay. Now, we tried a different cyclone here, the 3-product cyclone, to try and get around the problem of classification of UG2 in that secondary circuit. The 3-product cyclone is a conventional cyclone with an extra vortex finder inserted concentric to the existing one. So it gives you a normal underflow and 2 overflows. Okay, the 2 overflows, one contains middlings, and in this particular case, we needed to do something with the middlings. And what we did is we used a screen. The middlings went on the screen, 100 micron apertures. The oversize was reground. The undersize escaped and it was floated together with the other product. Okay, so because of this system, it adds 1 unit as opposed to just 1 classifier, which is the screen in that particular case. Okay, so this is just a picture of the 3-product cyclone and the schematic. I already explained what it is. You can see it's got 2 vortex finder. The one overflow comes through here and the other overflow comes through the other one. And this is just a picture of the actual cyclone in operation. Okay, so when we looked at the flotation results, it showed that the 3-product cyclone was much better in terms of the recoveries, the total recoveries, and no penalty in terms of the grade. You can see this is the conventional cyclone. The recovery was much lower compared to that of the 3-product cyclone. These are just different conical sections of the 3-product cyclone. And the grade were almost in the same region. So that was a better system compared to the conventional cyclone. And this is why. So the 3-product cyclone had more liberated particles compared to the conventional cyclone. Even those attached to sulfides were more and they could be recovered. Even those that were partially locked into sulfides were more and they could be recovered. But those that were attached to silicates and the other silicaceous materials that could not be recovered through flotation were fewer. You can see the conventional cyclone starts to dominate in those particle regime. And for those that are completely locked in silicates, they were quite a lot. And this is what explained the loss in recovery. So this is one system that you could use in your closed circuit grinding application to get around the ore constraints imposed by the chromite and the silica in the UG2O, okay? Still the same circuit, we can also do something different. We don't just have to induce or introduce a 3-product cyclone. We can go open circuit, okay? So by rearranging, instead of having that classification the way it is, we can do something different at that node. Because it still controls the product quality and reduces overgrinding, if we for a minute focus on reduction of overgrinding, then we can do something upfront. And this is the circuit here, exactly the same circuit. We haven't touched the primary, but the primary Raffatel goes to a densifying cyclone. From the densifying cyclone, the overflow bypasses grinding. The underflow is ground, but this grinding mill is now in open circuit. It does not require any closing classifier, okay, to achieve exactly the same. Well, many doubting Thomases would say, where is the data to show that this could work? Here is the data from a real plant. So you can see in this particular circuit, after changing the cyclone, we were doing 280 tons per hour, okay, in the primary. So this is fresh feed, crushed feed. Then after the first recovery, the overflow from the first cyclone went to about 260 tons per hour, okay? Then from there, in the secondary circuit, we introduced 260 tons per hour. But look at what happened here. The densifier underflow was 228 tons, okay? So about 32 tons or so bypassed the grinding circuit. And we were only introducing material that needed to be ground in that densifier. And the result is we were able to meet the percent minus 75 microns needed for that particular circuit to effect our recovery. And this circuit worked just well. However, be warned, the densification cyclone had to be tuned carefully so that the solids going into the secondary bore mill were at the correct percent solids, and also the fines were completely depleted, and it did the trick. The recovery numbers, no penalty in the recovery. These are just the size distributions from that particular circuit. You would see here that from the primary circuit, we had our feed, the bore mill product, the cyclone underflow, and cyclone overflow. This is the cyclone overflow that went to the, after flotation, it went into the secondary circuit. Look at how fine that densifier was, okay? It's very fine. So we took away all the fines that did not need grinding. And then this would be the densifier underflow, which was the feed to our bore mill. And this is the bore mill product. And when you combine with that densifier overflow, this is what the secondary Raffatel saw as a feed, and it did the trick. Okay. The last part I just want to quickly look at is, even when you have compression grinding operating in closed circuit, the same rules apply. This is a vertical roller mill that is operated in the closed circuit with the air classifiers, and this is from Warren Little's work. So a schematic that illustrates what is happening in here is, this is a grinding table. Okay, so this is where you are doing the grinding. These are the rollers, and the material is fed on the rollers. When it's ground, it's air swept, goes into the classifier. There is a reject stream from the classifier, and the product goes that way, okay? The beauty with this is when you control the flow rates correctly going into that air classifier, you can actually control the cut point, okay? And in Warren's work, he was able to control, we needed to replicate, can we use this closed circuit for primary grinding, tertiary grinding, and secondary grinding and tertiary grinding. And from his work, he was able to do that. You can see these are the PSDs. These mirror primary grinding, secondary grinding, and tertiary grinding. And all of these were subjected to flotation. And you can see here the energy split from Wen van Roenik, that the air classifier takes between 1/3 and 20% of the energy split when you use an air classifier in such a system, okay? So in Warren's work, these are the recoveries. You can see if you go to tertiary grinding with a system with the VRM to mirror a tertiary grinding, your recovery is very high, okay? It actually goes above 85%. Secondary grinding, it goes around about 78%. Primary grinding, it goes about 60%. So it mirrors what one would get using the conventional grinding. But what is good in here is you can precisely get the product that you need in terms of tuning the airflow rates to your classifier. Okay. So the goal when we use closed circuit grinding applications is, can we recover the material? Can we have sufficient capacity? And we can also look at the Traha curve. As long as we are within where the Traha curves allows us to recover the material, we are okay. If we can minimize the energy, let us push our product like we did in terms of screening. We can push our product to slightly coarser. As long as we can recover all the values, that is okay. A lot of work has been done in this, and the Grant Valentine and a student called Yuan did a lot of work on this, and they've showed beautiful graphs that say, even if your product from the screen may be coarse, actually when you look at the material of interest, in their case it was silver and lead, it came out liberated and they were able to recover it. Okay, so that would be the goal, to look at, can we recover it, not how coarse or how fine our grind is. By way of concluding, closed circuit applications are very important. We can't escape in our mineral processing, whether it's gold, platinum, copper. It is very important. They are always there. So how can we optimize them? We need to look at both the feed size distribution that we are feeding and tune our classifier to deal with the feed that we have, tune our mills to deal with the feed that we have, because the feed is king. It influences everything that happens downstream. And the Takwa example I presented shows that it is doable. We can tune the mill and the classifier, and we can get exactly the product that we want. Look at the classifier as well. And the classifier, while it does not consume energy, it does have an influence on both energy, throughput, and the grind quality. Okay? Screens give advantages in terms of energy and capacity by minimizing the recycle loads, but one should also look at the footprint. And they are failings when it goes to very fine apertures. Then the VRM, you can actually tune the classifier there to give you exactly the product that you want, and you can get good recovery out of it. So from this presentation, it is not the closed circuit loop that hurts production. It's how we attempt to harness it that determines whether we can get joy out of it or misery out of it. And I hope we all get joy by tuning both the mill and the classifier in these closed circuit grinding applications. Thank you.
Thanks a lot, Aubrey, for a fantastic presentation there. Quite enlightening, a lot of experience on the background. I think we're getting close to the hour here, but we can have a few questions. Please, guys, state your name there and announce yourself and raise your hand. But Aubrey, in the meantime, when people are warming up, let me just make a very short question that, yes, I think high frequency screens are attracting for quite a while a lot of attention there, as you showed, changing the game quite a bit as far as circulating load and everything. But when people look at most of the successful applications, we see very often associated to lead zinc type of ores, for instance, which are very dramatic differences in specific gravity between the different components, which is obviously a big advantage of using like a screen, which density plays a minor role compared to a cyclone where things are put you on the edge as far as over grinding. Can you just make a comment on your experience in cases where that density difference was not so huge and still screens were quite attractive?
Yes, they are attractive. The case I showed for the gold plant in Namibia, there were no density differences there. And in some copper plants where the plants are relatively low, they have actually introduced high frequency screens at 300 microns or 425 microns, and they work very well. The case I alluded to, and Grant is in the audience, he can comment a bit on it, the lead silver where there were density differences. There it's actually very good because you navigate the density issues that you encounter with the use of the hydrocyclones. And that is where in such circuits, I think it beats the hydrocyclone hands down. Yeah.
Oh, perfect. Thanks, Aubrey, for that clarification. And indeed, Grant is already with his hand up. And before passing on to him, I'd like to welcome him as the newest member of the GCC, officially already through the door. So please go ahead with your question, but already with your salute here.
Thanks, Marcelo. Yeah, and I guess commenting on Aubrey's question there, yeah, the case study in Mexico was a great example of where screens not only increased throughput by 20% by reducing the fines production, but also because of that density difference, there was actually, I think from memory, a 6% increase in recovery. So you got a 20% increase in throughput and a 6% increase in recovery, even at that coarser grind size. So yeah, really interesting case study there. Aubrey, I had a question. Thank you for the good presentation. The question I have is related to the screening work that you showed, where you had reduced screening efficiency at higher percentage solids. And I guess this comes to a problem that I've had to deal with recently, where we've got a constraint on the screen undersize density in the downstream process. And one of the things that I've been considering is the management of spray, but using spray to alleviate that high density feed. Have you had any experience in the use of sprays to kind of repulp halfway down the screen? And is that can that be sufficient to overcome the issues in high density feed and still maintain a higher density screen undersize downstream?
Yes, you've actually hit the nail on the head. When you do a repulper in the middle, it actually helps to alleviate that problem. But then you now have to balance the water. So the water, you don't put a lot of water up front, you stage it when you add on the screen. Then it helps you to get around that, yes. It's got a limit to which, beyond which it doesn't help, but yeah.
Yeah, thanks, Aubrey.
Very good point. Other questions from the audience? We're going a bit over time, but we can still accommodate a question or two. Yes, Holger?
Yeah, I have a question just linked to the former one from Grant. Do you have any experience with the pressure? If you add some water in the midstream of on the screen, how about the pressure? Do you go with high pressure then to agitate the material, or would you just go with low pressure, just sprinkling or just spraying, more or less spraying the water?
The circuits where they put repulpers, they make sure that you have an agitation system, a mild agitation system. So you repulp it so that it's not segregated anymore. It's like you are refeeding to next section of the screen, which is a well mixed feed again. I'm sure Derek have developed a repulper in some of their designs now. So they do supply a repulper if you have such problems with their high frequency screen. The one other good thing with this new high frequency screen, be it Derek or is it Lansky, what the material of construction for their apertures or the screening surface dilates a bit. So that dilation assists in avoiding clogging up. So when it dilates, it releases. However, the problem that comes with that is the measured D50 will always be slightly higher than the aperture size that they give you. It's because of that dilation on the screen surface.
Excellent. Any other questions? Yes, please, Anderson.
Thanks, Marcelo. Hi there, Aubrey. Thanks for the nice talk. I just have a more conceptual question to ask. So you mentioned quite early in the presentation that we were dealing with a very long sag mill, 12 meters long, I think. And so as a matter of principle, something, these mills are generally, in terms of transport, it's a very poor pump that's working in the wrong direction. So in addition to linking it in closed circuit with, say, a well-tuned cyclone, or even having your screening set up very efficiently, is there a question of liner profile that could also achieve some step changes? I was just thinking in terms of, you have a very long mill, and in terms of getting the pressure drop right in order to drive the slurry through this long journey, what would happen if you, say, change the liner profile systematically along the length of the drum? I could imagine that you could each stage such that the effective pumping mechanism is increased quite significantly. I'm just not sure what the sort of opportunity cost issues are associated with that. But just from a simulation point of view, from a DEM point of view, we notice that when you do things like that, you change the permeability quite drop, sort of goes through step changes in the right direction, which is essentially what you're looking for to drive your slurry with the right particle sizes through the system as quickly as possible. So I just wanted your thought on that, even if it's just to say it's a crazy idea.
So there are two responses in relation to that. The first one is when you go to cement mills in the cement industry, where they have long tube mills, they use liners, and the purpose is to have a graded bore charge. So that the bore charge is segregated, and that allows more permeability in terms of the dry mill when you use liners to segregate your bores. In wet mills, it's very quickly destroyed. It doesn't help much. So in grate mills, actually, the actual grate at the end is the king. But what you could do is the bore load that you use and the feed characteristics play a significant role in having that the permeability that you set up in the grinding mill. I think the Takwa example that I gave on the outset, there were a lot of things that we did on that Takwa to an extent that if I went through each of those, you can actually see that the classification was the list of the interventions. So there was one to look at the feed, two to look at the bore load, And 3, we had, there was a change in the liner design, but for a different reason. The liner they had was very aggressive already. So we had to tone it down so that we can balance the other things. But in the cement mills, they do exactly what you were suggesting.
Excellent. So any final question from the audience, or shall we let Aubrey go with a thanks from the group here, and of course a big hand for him. Thanks, Aubrey. So thanks a lot to everyone for coming, and really thanks a lot, Aubrey, again, for volunteering to give this fantastic presentation, putting together theory and practice, I'd say. And also, please come back next month, the 26th of May, for a final seminar, actually, for this first half of the year. So thanks, Aubrey.
Thank you very much, Marcelo, and thank you to the audience.
Indeed. Thanks, everyone, for coming. Okay, have a